Okay, now I'm going to tell you how to look for local minima and local maxima. So basically, it is very similar to what you saw in Mathematics 1, right? So the main theorem here is that if a function f has a local extremum at, well, which means either minimum or maximum at a certain point, then its partial derivatives are going to be zero. Um, the reason for this is kind of simple, right? So if you want to say, I don't know, for example, for minimum. So if you have a function of two variables, right, and you know that it has a point of minimum at AB, then if you restrict it, so if you fix y to be b, so if you consider a function of just one variable, so f of xb, then this point still has a minimum, right? Because still the value of f of ab is the smallest for the given value of x at a, right? But then if that is the case, if this function as a function of one variable has a point of minimum, then it means that its derivative um, at a is going to be zero. But this is precisely the partial derivative of x of ab, right? So this is basically the proof of this theorem. But you don't have to remember the proof is just a kind of to probably it is a good idea to understand it, right? So to make sense out of this theorem. Now, here is the definition, right? So if we have A and B and it is an interior point in the domain, so meaning that a small disk centered at AB belongs entirely to the domain of the function f, then this point is either a singular, I mean, it may be a singular point. So if singular point means that uh, either of the partial derivatives is not defined there, or it is called a stationary point if both partial derivatives are defined and equal to zero. And it is called a critical point if it is either singular or stationary point, right? So let me go through a number of examples. But before I do, let me just notice that um, the main theorem here works only one way, right? So if we have a local minimum or a local maximum, then the point at which we have a local minimum or local minimum is going to be a critical point, right? So cri, so which means that either stationary or singular. But the converse is not true. So it is possible that both partial derivatives are zeros, but the point is neither local minimum nor local maximum. Okay, so it is just what in mathematics it is called a necessary condition, but it is not a sufficient condition. Anyway, so let us look at examples. It's probably best understood through examples. So find all critical points of this function. So the function looks a little bit complicated. It's e to the power x times cube root of y minus x squared. Right? So to do this, we first need to find partial derivatives. So f partial derivative of f with respect to x is the following. So first we differentiate the exponential function, right? So its derivative is the exponential function itself. So it is going to be e to the power x. It is kind of easier to work with if I rewrite that cube root of x is really y to the power 1/3. It is going to be easier. So I'm going to just write y to the power 1/3 minus x squared times the derivative of this with respect to x, right? And the derivative of this with respect to x is y to the power 1/3 minus 2x. And fy is basically the same thing, is e to the x times 1 y to the 1/3 minus x squared times, now I've got to differentiate this with respect to y, right? And its derivative is going to be x times 1/3 times y to the minus 2/3. Okay, and here you need to understand that raising to a negative power is the same as dividing by a positive power, right? So y to the negative 2/3 is basically 1 over y to the 2/3. And it is important because now we see that this is undefined if y is 0. So if y is 0, this is undefined. So I'll write NA, undefined, not available. Right? So it means that if y is 0, then our partial derivatives, well, at least one of them is undefined. Right? So it means that any point where y is 0 and x is, well, basically anything, it doesn't really matter as long as y is 0, is going to be a singular point. Okay, so this is a part of the answer, that all points of the form x comma 0 are singular points. And we know this by looking at the negative exponent at y. Okay, if we have a point that is not singular but stationary, so it means that we need to equate both partial derivatives to 0. Okay, now notice that to do this, we can assume that y is not 0, because the case when y is 0 has already been considered, so we don't really need to think about it anymore, right? So if y is not 0, then we equate both partial derivatives to 0. Okay, and we see that, well, 1/3 is not 0, so this is not 0, so I mean we would just assume that y is not 0. Now, the next thing that you should probably remember, that to anything is strictly bigger than 0, right? So this part is just not 0, it is strictly bigger than 0. Okay, so which means that from the second equation, the only term that can make it to be equal to 0 is x, right? So if this is 0, then x has to be 0. And now we are going to substitute it to the previous equation, right? So y to the 1/3 minus 2 times 0 is 0. But then it tells us that y to the 1/3 is 0, which effectively means that y itself is 0. But we know that y is not 0, right? So it just means that, that there are no solutions. So there are no solutions. So it means that here there are infinitely many singular points. So the first entry is anything, and the second entry is 0, and there are no stationary points, right? So this is a contradiction, kind of. I will write something like the skull with bones. This represents contradiction, right? So this is contradiction. Contradiction to the assumption that, well, y to that y does not equal to 0, right? So this contradiction means that there are no stationary points. Okay, so and that's basically it, right? So the answer is that critical points are x comma 0, where x can be any number, and all of them are singular points, but there is no stationary point. Okay, and here is another example. So notice that in example 2, we're supposed to not just to find all stationary points, but to determine whether each of them is a local maximum, a local minimum, or, well, neither one. So which means a saddle point. Now, again, just like in the first part of the lecture, I am going to work it through by using some kind of common sense and a little bit of Genian guesses. But in the next part of the lecture, you will see a systematic procedure that you can apply to figure out the type of each critical point here, right? So at the moment, we only have a procedure to find critical points, right? So to do this, we equate both partial derivatives to 0. So f partial derivative of f with respect to x is what is minus 2x. Partial derivative of f with respect to y is 2y minus 4y cubed. Then we equate both of them to 0. So notice that here both partial derivatives are well defined for all values of x and y. So we don't have this kind of issue like in the previous example. So we do not have singular points here. So all all critical points, if they do exist, they are stationary points. Okay, so from the first equation we get that x is 0. The second equation we probably, so let me divide it by 2. So y minus 2y cubed is 0. Then I guess I can factor out y. So y times 1 minus 2y square is 0. This is the product of two factors. So for the product to be 0, either of the two factors must be 0, right? So it means that either y is 0 or 1 minus 2y square is 0. And in this case, I'm going to move 2y squared to the right-hand side. So 1 equals 2y squared. So y squared is 1/2, which means that y itself is going to be plus minus 1 divided by square root 2. All right, so notice that x is 0 in any case. So what we found is that there are three critical points. So 0, 0, 0, 1 over square root 2, and 0 minus 1 over square root 2. So there are three critical points here. All right, so here basically we derive the gradient, and here we derive the critical points, or this, well, all of them are stationary points. And now I am going to tell you how we can figure out for this problem which of them is a local maximum, and which of them is a saddle point, and which of them is a local minimum. But again, so what I'm going to do now is not really a systematic procedure, because it can't really be applied to other types of functions, right? So in the next part of the lecture, there will be a systematic procedure that you can just kind of blindly apply and get the answer, well, most of the time. So here, now I am going to show that the stationary point 0 and plus minus 1 over square root 2 are local maximum. So how do I do this? So to do this, I am going to use the trick from secondary school called completing the square, right? So I'm going to write it f of x, y. I'm going to change it a little bit. So I'm going to write minus x squared minus y to the 4 minus y square in parentheses, right? So okay, so now I'm going to take this part and complete the square. Complete the square. Well, to complete the square, so this is minus x squared minus, well, y to the 4 is really y squared squared, right? So I'm going to have y squared minus something squared. So what should I write here? Well, whatever is written here, this y square is really 2 times y squared times whatever is written here. And since it is just y squared, I should write 1/2 to get y squared, right? So which is why this is 1/2. All right. Well, at the same time, y squared minus 1/2 squared is going to be y to the 4 minus y squared plus 1/4, right? So in order to compensate for including this 1/4, I need to, well, it is actually subtracted, so I should write plus 1/4. So now it should be correct. So now it should be correct. All right, so now I have just completed the square. So the next thing to do is to understand that, well, negative x squared, well, x squared is always a non-negative number, right? So minus x squared is a non-positive number. So this is minus something squared, and again, it is a non-positive number. And in order for the whole expression to be maximized, the only way to do it is when both x squared, I mean, so generally speaking, for most values of x and y, these expressions are just negative, right? So, and in order for them to be maximized, we want them to be exactly zero, because the alternative is that they're just negative, right? So in other words, x squared should be 0, and y squared minus 1/2, um, well, x, so sorry, x should be 0. Uh, for the whole expression to be maximized, x squared should be 0, and y squared minus 1/2 should also be 0, right? But this precisely gives us these 2 points, right? Well, x is 0 and y squared is 1/2. I've just solved it, so it means that y is plus minus square, well, 1 over square root 2. Okay, so generally speaking, the whole expression is less than or equal than 1/4, and it is only equal to precisely 1/4 whenever x is 0 and y squared minus 1/2 is 0. Okay, so it means that the stationary points are not just local, but actually global maxima. This is what we've just shown. They're not just local, but even global maxima. Okay, right. Now, how can we see that the other stationary point, which is 0, 0, is a saddle point? Now, so first notice that f of 0, 0 is just 0, right? So if you replace x with 0 and y with 0 in the equation, you will just get 0. Okay, so now I'm going to use a different form of my function. So I'm going to rewrite my function as f of xy as minus x squared plus y squared times 1 minus y squared. And then I'm going to do a little trick, right? So to prove that this stationary point is a saddle point means that to show uh, that there exist points xy with small values of x and y, I mean close to 0, with both positive and negative values of the function f, right? So because the f of 0, 0 is 0, right? So, and to show that it's neither minimum nor maximum, we need to show that there exist both positive and negative values in a small neighborhood of the origin, right? So how do we do that? So basically the idea here is that to notice that the first term is negative and the second term here is positive, right? So if there were no second term, so which means that if we set y to be 0, so f of x0 would be just minus x squared, and it is strictly negative as long as x is not 0, right? So if x is a small non-zero number, like let's say if x is a small non-zero number, then this would be equal to minus epsilon square, and it should be negative. Well, at the same time, if instead x is 0 but y is not 0, then this whole thing would become y squared times 1 minus y squared. And notice that this is going to be strictly positive as long as y is not 0, and as long as this part, 1 minus y squared, is positive. So which means that y should be like between negative 1 and 1. But again, as long as if y is a small number, so if say if y is like epsilon and it is a small number, then this whole thing is going to be like epsilon squared times 1 minus epsilon squared, and this is positive, and this is also positive, so the whole thing is positive, right? So it means that in a neighborhood of the origin, there are both points with values bigger than that at the origin and smaller than that at the origin. So therefore, it is not neither minimum nor maximum, and it has to be a saddle point. So that's basically it. So this is how we can check that it is a saddle point. But again, so let me emphasize that we only did it for this particular example. So this technique of completing the square and kind of substituting 0 into x and into y may not work for other examples, right? So for other examples, we will need a more systematic approach that we will develop in subsequent parts of the lecture. So here is the graph of the function. So, I mean, for your information, so there are the points of local maxima are here, and the saddle point is somewhere here. Okay, so now please do the quiz and proceed with the third part of the lecture.